We're finally at the final session of today's program. It was really a full day, but we're closing off with a great presentation. He's our second distinguished speaker who's just arrived from London to be with us. He's certainly proof that once a Koç University connection is made, it continues to resonate like a perfectly coherent quantum state. Well, Professor Mete Atatürk, head of the Cavendish Laboratory at the University of Cambridge and recipient of our Medal of Science, Koç University Rahmi Koç Medal of Science, is a global leader in solid-state quantum systems and quantum optics. Please join me in welcoming Professor Mete Atatürk.
Thank you very much. It's always a pleasure to be here. It's not my first time, so I have many friends in the audience, so it's quite a welcoming place. But it's very nice to see others here as well, others that I respect a lot, in particular in this field. So it was very nice to share the stage with them before. I'll talk about I picked the title "Communicating in the Quantum Era." This is not a hype talk, right? This won't be a hype talk. I'm not going to say in the new quantum world we are going to do things differently, but we're trying to do things differently. And the message I'd like to put forward is I'll focus on quantum networks a little bit. So because you had different topical coverage of quantum technologies broadly, so I'll focus a bit more on the quantum networks, what they can do for us. I'll be honest about what they may or may not be able to do for us. And at the same time, hopefully the subtle secondary message is quantum is just another emerging technology. Yes, it might be a bit harder because these things are a bit more sensitive sometimes, but it does contribute to society, both in terms of, at the very least, in terms of generating talent, but also in terms of generating new technologies. And some are hidden. If more and more we use them, they kind of get, they fall off the headlines, but then they're used routinely. So I'll try to highlight a bit. I'll also try to, given that it's the end of the day, I'll try to entertain a little bit. So let's see if I can manage that. So some of you might have seen this before. So this is I'm a physicist, so it's a physicist's very simple view of how things happen. All right. Two red blobs, I'm allowed to take red blobs as my physical objects. Two red blobs collide, interact. That's the universal sign of interaction. And then they go their ways, right? So two particles, you can imagine, they come in, they collide, and then they go their ways. If that collision, that interaction, is of a particular type, which I won't say what it is, but let's say that it's done in such a way that the internal degrees of freedom of the red blobs, what goes on inside the red blobs, are correlated, are affected from the scattering in a particular way. That means once the balls are out there, independent of how far they are from each other, that correlation will sustain. There's classical correlation we can anticipate, but then there's quantum correlation, which caused a lot of problems for this kind of a setting for Podolsky and Rosen. And then they went to Einstein and said, look, this doesn't make sense. He joined in, and then they wrote a paper called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" ? Obviously, you can anticipate their answer was no. Otherwise, why would they write that paper? And they were worried about the fact that correlation has an effect for both particles without any dependence on the space between them. So what happens in one local reality seems to affect what is going to happen in the other local reality based on my choices as an individual in one local reality. So that was the problem paper. Now, of course, not saying quantum mechanics is wrong, but it is pointing out an issue that quantum mechanics had to resolve. And then, of course, a response came from Niels Bohr, same year. And the title is "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" And now you can imagine the answer isn't no. It is actually, but it's also not yes. So it's not a no, but it's also not a yes. It's basically saying, don't ask those kind of questions. Is basically the main answer. Ask different kind of questions consistent with non-local realism as opposed to questions consistent with local realism was the thing. But the thing I want to focus now is not so much what happens to the two particles after they collide. That the non-locality aspect is the reason why all that conversation happened, and then many letters between them, and then much research afterwards as well. practical as well as perhaps more on the philosophical side. But I want to focus on that interaction part of it. When the two particles collided, something happened to create that correlation. So correlation generator required in the end, it doesn't matter how far apart the particles are at the end of the day, they had to be nearby. They had to come together. It's called proximity. Whatever physical mechanism that generates correlations between those two particles is going to dictate its own length scale of interaction. What proximity means for us. Two black holes will interact with each other. That's not the same length scale as two electrons interacting with each other, but they all come with their own individual length scales, given given a particular type of interaction that might generate correlations of the internal degrees of freedom. Any physical phenomena requires a characteristic length scale. It requires proximity, except one. So there's only one that I'm aware of that we can kind of beat it, and that is if the two red blobs can exchange energy through radiation, for example, where they don't necessarily have to be close by to be affected by each other. They just have to be, in technical terms, they have to be sharing a common mode, a common optical mode. So as long as the two red blobs sit somewhere in the universe where there is a clean optical mode that they share, co-share, then this interaction could be turned on. So for the first time, we now have interactions between two objects that do not depend on how proximal they are to each other. So any object can be relevant for the other object as long as there's light providing that interaction, a mechanism to provide that interaction. That requires only one thing, common mode, but line of sight. Now, quantum physics gives us one more thing that's really counterintuitive, and that's called a concept called quantum erasure. In our daily everyday lives, if I want to make a measurement, there's a reason for it, because I want to know what the answer is. For quantum erasure, completely counterintuitively, I want to make sure I don't get the answer. That's why I'll make that measurement. It's a quantum erasure measurement to make sure you don't get the answer, but no one does either. You're properly erasing the information by doing measurements. That's a bit odd. But what it turns out to be, as a useful item, is that if I have two red blobs, both glowing, or maybe probability of glowing, and the eye, the third party, makes a measurement in such a way that the information about who emitted the photon, you can create entanglement between these two guys. So you can create correlations between those two guys. And now the difference is, unlike here, they don't even need to share an optical mode, a common optical mode, or have line of sight. They may not even have any idea that the other one exists, but they might end up being non-locally correlated without ever being close by, because there's a third party, a puppet master, if you will, that is able to look at two red blobs in its own way, replicating this, to create correlations between them by a particular quantum mechanical measurement called quantum erasure that is able to do. All right? That's very odd. All right? That's a very odd concept. Things that are not proximal can be correlated by a third party, almost weaving out correlations step by step. Imagine this picture. Extrapolate what we just talked about into this picture, where independent of where the red blobs are, there might be lines connecting them, and not necessarily stronger because they're closer, but stronger because we chose it to be so. So we can actually talk about creating perhaps a collective phase, a new behavior in matter, without the basic requirement that electrons have to be proximal to other electrons, or a particular atom has to be nearby another atom to couple dipolarly, a spin has to be near another spin for magnetism. You can actually, if you could do this, I don't know how to do it, I have some ideas. If you could do this efficiently so that you can scale it to thousands and thousands, you can study a new concept called matter without topology, a matter without the requirements of where the particles themselves are, how they orient themselves. All right. But to be able to do any of this, so this is motivating how to link many quantum objects together by light. You can see why this is going to be a quantum network. I'm motivating how to do this from a purely physics perspective. Not applications, not what it will do for us as a technology, but purely by physics. I'm saying this, if you can do this pairwise weaving, you will be able to study condensed matter phenomena, emergent phenomena without topology. I think that's fantastic. So what we need to do is get to this blob. We have to make sure that we have blobs that we can control and isolate. And I'll take you to these two Nobel Prizes that were given, very rightfully, I think. The first one, Demelt and Paul, they were the first ones to actually trap a quantum object, hold a quantum object isolated from the rest, completely contradictory to Schrodinger's statements. Of course, we'll never be able to see a single electron. Of course, we'll never be, it's ridiculous to talk about a single atom. They always come in large ensembles. But if we could, then we could do a thought experiment. Well, they did the actual experiment, isolating a single trapped ion in vacuum by electromagnetic forces. And De Weyland and Serge Roche took that isolated quantum object and really used this quantumness, did coherent control, and demonstrated that it can be used as the red blobs that I was talking about before. All right. In fact, there is one funny thing. After being able to trap a single ion, Demelt changed his signature to include the actual conceptual design of the trapped ion. So those are the gates, electrodes that trap an ion. Ion is the dot in the middle. That's the quantum object, right? So he changed his own signature for it. So that's the dot. This is from our colleagues in Oxford, trapped ion. These are the electrodes. And that little dot here is the trapped ion. That's the quantum object. And I want to take a moment. We talk about quantum, the number of qubits, the quantum systems, quantum computers. Take a moment to appreciate that that is a singular, isolated quantum object. And we're looking at it. We're looking at it by light directly. And that is very new. Yes, exactly. You can see it. It's right there. It's almost, for quantum technologies, it's the pale blue dot moment, right? It's right there. You see it and you know there's a single quantum object. It will be completely counterintuitive to you when you start talking to it. That's the point. So we have these objects to work with. But can they be useful? Can these red blobs be useful? I'm going to take you through this slide. Does anyone know John Arnold, who John Arnold is? Or the Arnold clock? That's the Arnold clock, or the Arnold at the time. This is before Arnold Schwarzenegger. John Arnold basically made the best clock possible at the time. He had the highest precision. And when they discovered, the Royal Observatory discovered that this is the best clock. This is actually a pretty decent clock. That became the golden standard. So what ended up being was around London, mostly around London, when people needed accurate time, think about it, you don't actually have a good clock around. So you don't actually know what time it is. We might all agree that it's 3 o'clock right now because we have a common clock, but in reality, it may now be 3 o'clock. Well, Arnold pocket watch was able to be precise down to 10th of a second. 10th of a second. So Ruth Belville, has anyone heard of Ruth Belville? Notice that next to Ruth, there's Ruth. Look at this, the time. The sign says the time because Ruth held John Arnold's pocket watch. It was hers to keep. It was hers to go around London to anyone who's paying, companies and shops and all that. Anyone who's paying, she would go and sell time. She would tell them exactly what time it is so they synchronize to the right time. Right? That's not this 18th century. If you think about it, it's not that old. And then, of course, after Ruth, her daughter picked up and continued onwards until 1940. So the last person who sells time in London retired in 1940. Fairly recent. So this is a case of communicating the precise. And here's a little storyline of the clocks, the timeline for clocks. Sundials are they're off by 50 minutes a day. Okay, they roughly tell you it's night and day and it's time to eat. Pendulum clock is 1 second every 2 hours. That's pretty big improvement. 1 second, it goes off every 2 hours. And then it goes down to the first commercial quartz oscillator, 1 second in 8 months. So it's accurate to the second for 8 months. It's when she lost her job, basically, selling time. And then there was a revolution. The revolution came with, right after the war, with something called the atomic clock. This is now, every clock has a resonator, something that beats. Metronome is a beater. Quartz, oscillator, the name says it, oscillation. An atomic clock looks at the internal degrees of freedom of the red blobs that I was talking about. It looks at the atomic transitions, and that's, if you do it right, it can be very precise. And they were able to show that orders of magnitude better timing precision when it comes to this. Today, this looks slightly more complicated perhaps. I think this is the state of the art from Junier, from Jilla at Boulder, Colorado. It's off by, its frequency is as good as 10 to minus 20 hertz. So it will take 10 to 20 seconds for it to go off by 1 second. This corresponds to being able to tell, if you can tell time so well that it actually becomes a problem, because now you realize that your clock is not measuring time, it measures space-time. So relativity kicks in, and over 100 microns separation, he's able to see the difference of gravity and therefore time. So when you, this whole time, you can actually ask one question, what time is it? And you get an answer, more and more precise answer, until we get to Junier, where he cannot tell you time anymore. So what time is it? He has to say how high. And only at that value, of given value, he can actually code a time. And that's all quantum, right? That is all quantum technology to the point where we now have clocks that we don't actually need the accuracy for. But we can do fundamental science to understand what's going on. And also it helps with any kind of fast pace that we're operating today. So that is, Ruth was communicating the precise, communicating the accuracy, communicating time in a precise way. Quantum networks, of course, she was going from one place to the other. Today, what you can do is you can actually buy that time, literally buy that time, by simply tapping into the network that National Physical Laboratory and US NIST, for example, PTB in Germany, they provide this time standard, so everyone can tap into it and learn. So the concept of translating or communicating time and communicating precision is what the atomic clocks are achieving today. There's another thing you could ask. You say, how about communicate security for me? How about let's communicate but securely rather than precisely, necessarily? And these are collection of citywide, metropolitan size quantum networks, meaning there are different locations where light, again, same concept, red balls exchanging light. And all this communication is done through light. So there are multiple nodes, locations, where light goes from A to B, and it's generated in A, detected in B, and it relies on quantum mechanics principles of being absolutely secure because of you're not able to clone. So you cannot eavesdrop, you cannot tap into the signal. Many variations of the concept, but you can see that it's actually around the world. This is, there's Europe, there's US, China, and many more coming up as well. This is the UK version. I'll highlight this as well. So there is a quantum network, metropolitan size, 410 kilometers of quantum network from Cambridge to Bristol. It's a single line. There are trusted nodes in between. So these are well guarded by real people to make sure information doesn't leak out, but otherwise it's secure all the way through. And in the two ends, in Cambridge and also in Bristol, there's a network, local network as well. So Cambridge has a 3, this is 3, but now there's a 4th one added. There's a 4-node network. Bristol also has something similar, so that you can do local communication there, and then you can send the information out in a dark fiber system to Bristol all securely. What can you do? Why would you want to send secure information? This is one of the applications they picked. This may or may not be the right one, but there's one application where security of personal data, medical data, is important. So purely through secure communication, quantum communication, they were able to send MRI signal between Bristol and Cambridge, from Cambridge to Bristol, between two connections, and absolutely securely, verifying that it's secure communication, no one can tap into it, and that signs off the requirements for NHS, for health, national health system. But all of those I talked about, it basically operates in this format. It's I call these the first generation quantum networks. It's QKD based, quantum key distribution, secure communication, information sent by A, received securely by B. That's it, and then the protocol stops. But there's an alternative, and that's what if information is sent by A, but then that information is stored by B, and then at a later time distributed to C and D, and so on and so on and so forth, all secure, but also all quantum. And the difference now is the channel had to be quantum. The channel that transmits that information had to be quantum. The nodes weren't. The nodes were me, right? I'm not quantum. But now, if we want to do this second option, the next generation quantum networks, we have to have not only quantum channel, but also quantum nodes. So you have to replace the individual that receives, or a detector that receives the signal, replace him with another object, another red blob that receives the information, quantum information, and manages to store it or redirect it or do something with it. Right? So that's the challenge. This is a paper from 2008 by Jeff Kimball, sadly passed away last year. But he did a great job. He basically showed us exactly what to do. He said, quantum channel, red arrow, quantum node, box. That's it. Go build it, right? You just have to figure out what box means in real life, and the red channel is in real life. This is a slide from Optica's 2020 roadmap. Used to be OSA, but formerly known as OSA. Optica's roadmap on various quantum technologies covers what I talked about, atomic clocks. You can see that 2025 were GPS-free navigation. These are tests happening right now. So this is all happening. Medical imaging is the direction that they're going in through gravimeters, being able to measure gravity as you hover over something and seeing underneath. There's this part, the quantum computing part. So they're expecting fault tolerance by 2035 plus. So that's we don't have to immediately deliver to 2035. There's a plus there. So maybe that's all intended. But on the communication side, the red, there's quantum random number generation that has been done. Key distribution has been done, as I've demonstrated. There are plenty of metropolitan city level communications going on. It just needs to be extended and scaled. But the quantum internet part that came from Jeff Kimball's vision is still quite some time away. And hopefully I'll highlight some of the reasons. It is important for a country to say, a nation to say, what is for such an emergent topic? Same with AI, same with others, semiconductors. When things are critical, you need some sort of guidance as to what it is you're prioritizing and what the goals are. And this is what the UK did among many other countries as well. They set up 5 missions after having invested in quantum technologies for 10 years. They looked at what the landscape looks like, and then they identified these 5 missions in consultation with the community. And what you're seeing for quantum network is a world's most advanced quantum network at scale, pioneering the future quantum internet. I don't know what that means because there's nothing quantitative in there. So as long as we build something, I guess that's okay. But that's the goal. So there needs to be some sort of a push of what it is that we want to do on a national or international scale. So coming back to these red blobs, the quantum objects, trapped atoms were the first one we talked about, the strontium clock or others. They're still atomic systems, but there are many other systems, Josephson junctions, where quantum advantage was discovered, among others. But also we have spins and we have photons. And what makes a quantum network work is this combination usually. So if you want a recipe, that's the recipe. You want the photons for the quantum channel, and you want the spins, ideally, some sort of spins as the local quantum node going forward. So a quantum network would look like this. Again, these nodes are there with quantum channels in between, and each node might have more than one qubit. So each node might be a collection of these red blobs, collection of these quantum objects that interact locally with each other. Typically, there are 3 ingredients. You have flying qubits, of course. You have the processor qubits per node. It could be many. And you have the local registers, because this is the next generation quantum networks we talked about. You need to be able to store the information, dump the information somewhere, keep it quantum while you're doing something else. And when it is time, because other nodes are now ready, you go back and extract that information and continue. Concatenation is something you need to be able to do. So these are the three ingredients for a quantum network. And typically these are, as I said before, these are photons, spins. And if you're talking about a material, the register lends itself easily to something that exists in most of these materials for free, and as in some cases as a nuisance, and that's nuclear spins. So if you're dealing with a spin-based system, then the electronic spins are good for control and operation, but nuclear spins are preserved, they're a bit hidden, they don't interact with the environment that much. But if you can make this interaction strong enough, the electron talking to nuclear spins, you can efficiently write in and write out without losing the information, so you can store for a long time. So which material is the right material to pick going forward? Well, there are a dime a dozen. There are too many materials, and there are too many quantum objects in solid state systems, in materials, because they tend to be defects, actually. That's the interesting thing. It's not that a material, if you can make it better and better, you can get a quantum object. In fact, it's the opposite. If you make a material worse, you get a quantum object, which is quite ironic. But I'll cover that in a second. So you get a whole bunch of these materials, and if the material that you're working on today isn't here, it's in here and more option. This is just my selection of few, but there are many, many more. So just to give you an idea of what your options are, if you're working with, say, spins in silicon or diamond, there are only a few spins, and they interact weakly with the electron. If you're working with, say, semiconductor quantum dots, there are tons of nuclear spins, and they interact very strongly with the electron. So the physics of the quantum node you're building is going to depend heavily on what you pick as your hardware. And each one brings its own science to study separately. But they all work. They all offer some sort of a way to make it work, way to make it a quantum network, essentially. So, but which one do we pick to make it scalable, to make it large? Typically, there are certain things you need to check. In your material, this is what your defects are going to look like that disturb otherwise your material, vacancies, dopants, whatever. You need to do some sort of be able to tune these guys. You need to say, be at this wavelength for the light, be at this separation for Zeeman separation for spin, and also mechanical properties. And you need to be able to control it, coherently control it, like Wineland and Harosh, and that would be either microwave control or optical control. Right? These are the tools that we have available. That's our quantum optics toolbox, essentially. And then you have to go through this truth table, essentially. You have to say, well, there are flying qubits and stationary qubits, the spin and the photon side of the node, and these are the optically active qubits. And you have to look at all these properties for these systems. And if I go extend it there, if it's spin, there are certain properties it needs to have. If it's optics, there are certain things you need to check to make sure that the optics is fine and decent. And if it's a quantum network, then you have to combine those properties. Spin alone is not good enough. Photons alone is not good enough. They both have to be able to work together. They both have to be good. This is a beautiful map, brain map of things you need to do if you want to discover the ideal quantum emitter or ideal spin-photon interface. These are all the things that are available to you from materials. And this is all the things you want to do with these systems once you have it. And in between are all the different properties that you can have. And you can imagine that AI could be quite useful in figuring out the right combination for these systems. But it's a lot of work. The main message is it is not easy to find the material that works best immediately. But I will pick diamond because I like it. So the material I'll cover for the rest of today is diamond. And not this diamond, of course. These are our diamonds. They're extremely clean. They're mostly carbon, except for an occasional 1 or 2 atoms displacing the carbon atom. And we choose which atom to actually introduce as a defect. Kind of we cheat from this cheat sheet, if you will. Yellow color comes from silicon in diamond. Diamond doesn't have color. Yellow comes from silicon. Bluish color comes from boron. Pink comes from nitrogen. And that's a good one to start with. Nitrogen being abundant. Nitrogen vacancy centers are the most easily found color centers. So this is from the National History Museum in London. These are all different diamonds doped with different elements. And if they set it up really nicely. So if you ever have a chance to go to London, go and see this display. you can actually do the experiment. You can do a photoluminescence experiment in the museum. This is UV illumination of all those diamond pieces, and they all glow at different colors. So you can tell, this is the truth table. This is your lookup chart for what color comes out if I put a particular defect into the crystal. And you get to see that there are hundreds and hundreds of these. Diamond is able to host with wide bandgap hundreds of these optically active color centers. The most prominent one is the nitrogen vacancy center. This is, as I said before, one carbon is replaced by nitrogen, and nearest carbon is replaced by nothing. It's a vacancy, right? And that turns out to be just like an atom, just like a trapped atom. It's trapped inside diamond, so it doesn't go anywhere. And it's got optical transitions like the atoms. Its optics is not as clean. Optical spectrum is not very nice. So on our table, we would have eliminated NV center, but its spin is so good that it kind of compensates. And this experiment, this quantum erasure experiment that I talked about, essentially what you do is you excite two of these color centers, two of these NV centers. One photon comes out from them only, but you don't know which one emitted the photon. But if you emit a photon, you flip your spin. So spin is related to the photon that came out. And this magic equipment called beam splitter is all you need to erase the information of where the photon came from. If I do this, that's a quantum erasure experiment, essentially. And that means I cannot know which of the two NVs, distant NVs, emitted a photon, so they are entangled. That is the way to do this weaving of entanglement between two quantum objects, two color centers. And this is the experiment I like to highlight, followed by a reference here for the 3-node extension of this. But two NV centers in two different locations, A and B, are measured by a third party, C, to entangle individual spins in little chips of diamond at a distance of 1.2 kilometers from each other. That was the first time a solid-state system was used to demonstrate distant spin entanglement based on quantum erasure. And that is the starting point, actually, and almost a blueprint for how quantum networks are being built today. There are other color centers, as I promised. It turns out that this particular group, called group 4 color centers, which is, in retrospect, it's not that surprising. It's carbon-based, so every one of these elements behave roughly the same way. The values are slightly different, but their behavior is identical. They all produce color centers. They all look great. Look at this emission now. It's much narrower than the NV center, so it's more suitable for that single mode that we need to exchange. Spin is there, so the level structure looks like this. So this is the optical transition you would have. This is spin orbit splitting. So it's a single particle in a double potential well. Think of it that way, as undergraduate physics. Double well potential, single electron, and these are the two orbitals for that. You apply a magnetic field, you get Zeeman, and if there's a nuclear spin nearby, you get hyperfine coupling. So if you apply microwave fields, you will be able to drive these split transitions. And here's a nice result that shows the splitting exactly. This is due to the silicon atom's nuclear spin, silicon 29, and this is optically detected magnetic resonance. So you're driving a single spin inside diamond, and you're able to see its nuclear spin coupling as well. And this is the coherent Rabi oscillations, or how coherent it is. And clearly, this is not very nice. This wouldn't be it's not a good boasting signal to build something on. So you want to find out why this is the case. When you do this, here's a measurement of how coherent the color center is a function of temperature. But look at the x-axis. It is 2 degrees. It is an experiment done over only 2 degrees, around 4 Kelvin, and the coherence changes dramatically. So there's a very strong phonon coupling in the system. There's a very strong temperature dependence, even at 4 Kelvin, which was a surprise at the time. So what's happening is these replica modes, these orbitals, are actually creating phonon scattering that scrambles your phase, so you lose the quantum coherence available. So you got to fix it. So one way to fix it is you cool down further so there are no phonons. That's one way. We still have some room from 4 Kelvin down to millikelvin. Or you increase the splitting so that you don't see any phonons at that energy, so you don't get that scattering. So I'll show you the first one. This is the brute force method, or for those who know, I call it also the blue force method. That's the dilution fridge company that makes 7 millikelvin fridges. And that's what happens when you take diamond, same chip, and cool it down to millikelvin temperatures. Coherence goes up all of a sudden from a few hundred nanoseconds to 13 milliseconds. And that's just by cooling better. That's it. Still optics, still spin, but tens of milliseconds coherence means you can now start thinking. I highlight these 3 papers always as the blueprint for quantum networks with diamond color centers. 3 papers back to back, all 3 from the same group, effectively saying this is how we do quantum communication and how you build up quantum networks with active nodes based on silicon vacancy centers in diamond. And this is the latest thing that they've done. This is blind distributed quantum computing. So it's not quantum communication, quantum computing. Distributed because qubits are in different locations, only by exchanging light. And it's blind. And the story there is, if there is a quantum computer, it's going to solve my problems. But actually, sometimes question itself is more valuable than the answer. I don't want people knowing the question I'm asking because they know a valuable question. So quantum physics allows us to actually do it in such a way that the question is asked without the computer knowing. That's another oddity that quantum physics gives us. So normally you have to say what your question is, the computer has to understand it and then produce the result. In quantum physics, we can operate in such a way that it produces the result, doesn't know what the question was, also doesn't know what the answer is, but it communicates it back to you. That's what I meant by not measuring at the end and done, but simply doing some operations and then passing it on without looking. And that's what a blind quantum computing does. And they've demonstrated this with diamond chips over metropolitan Boston, 35 kilometers distance. So the client, the person asking the question of 1 and 2 qubit gate operations, is actually somewhere around here, asking the connection between them is over 35 kilometers away. So again, another concept of why we don't need proximity in quantum physics plus spin photon interfaces simultaneously. And there's more fun at the bottom. The second option, instead of simply cooling down, the second option is, can we do something to separate the gap so that the second replica is irrelevant? Yes, you can literally go down the periodic table, and it turns out that splitting just simply scales by the mass of the atom as well. So it comes for free. So by the time I'll go quickly on this, by the time you come to tin, you can actually operate here. You can operate, there we go. You can operate at 1.7 Kelvin with the same quality. You don't need a little fridge to run. And if you work with lead vacancy center, it's at 4 Kelvin, you use a little pulse tube cooler. All right. So there are opportunities over there, but you can do more. So this is tin vacancy center instead of silicon vacancy center. Just a simple change of the atom. Slightly different color, same properties, same level distributions, but now this is way more, 850 gigahertz. And if you apply a bit of strain, 0.1%, maybe not a bit, a lot, but this if you apply some strain, you can push it up to 1.5 terahertz. When you do that, you can actually get very nice performance, let's say, of your quantum object, as opposed to being something that's modest, just about showing Rabi oscillations, to 99.4 Rabi fidelity, millisecond time scales again. And this is operating at 4 Kelvin. So all of a sudden, it's a practical way of doing this experiment as well. And what you can do with these, you can actually put them into waveguides. Diamond, we now know how to shape diamond into very small nanostructures. You can shape them into waveguides. This is a optical image of these waveguide chiplets. And this is a tapered fiber. So this is inside the cryostat. This is all glue, sadly. This is tapered fiber. Fiber comes in and collects light by simply proximity, collects all the light in and out, and that's the only communication we have directly, and it produces the photons that we want, and the spin that's inherent is already behaving well. And by doing mechanical tuning, that's the advantage of diamond. By mechanical tuning, by changing shape, by actually bending diamond a little bit, you can really tune the optical properties. And here's, I put as a comparison, I put hexagonal boron nitride. I know people are working here as well, where a bit of stretching the hexagonal boron nitride tunes the color dramatically. So these are very valuable tools to have practically. Electrical tuning is also another operation. I'm putting, again, quantum dots, a different physical system as comparison, but you can tune the exact color to make sure that across a whole network, they're all of the same color. and therefore they can all share a single common mode across a metropolitan city effectively. And then when you put them into integrated circuits, you leverage all the knowledge you have from photonic integrated circuits without quantum, and you say quantum just comes in as a small chiplet that attaches, integrates, rather than a whole brand new, completely new way of doing things. I'll finish with that with some thoughts, and hopefully that will start some conversations as well. First of all, which one question? I did pick diamond, but I don't really have a good excuse, good reason, because all of these are also reasonable as well. The main problem is we don't have the one, and I underlined have, because we don't really make them. This is what nature gives us. The advantage the superconducting qubits had was that they were making them, so they could look back and then say, this is a bottleneck, let's change it. And they change their design. I cannot change my design as freely. I cannot tell the defect atom to move left a little bit, right? That's difficult. So we're bound by what we can have mostly, as opposed to what we can make. I wish we could make, and that might be an option for that. Second is, you see all these alternatives there. Exploring alternatives is always a good and a bad idea. It's a good idea because there might the correct system, physical system might be out there, but it's a bad idea. That means you're not investing into one effectively. You're not investing into one the way trapped ions were invested. If something had to be fixed, the whole community fixed it and moved on. Whereas in this research outfit, if the material doesn't give you exactly what you want, you say goodbye and you go to the next material. So there's a bit of the element of that, of quick fire. And third is reaching material maturity always takes time. And same as classical computing, quantum networks, sensors, material maturity is going to be key. Foundry concept, whatever we're doing, whatever technology we're doing, we should be operating at a industry standard, academic research standard, foundry type alignment, as opposed to everyone doing their own little tricks in their labs. And to reflect on the quantum networks, we have to identify the killer app, and I don't think it's out there yet fully. I don't think that all of these are possible. Communications, computing, I did show example of first blind quantum computing, distributed quantum computing. It's going to grow. That will be the way forward. But we don't really say this will solve the greatest problem if we had a quantum network. So we have to be careful about identifying where the application is. Second, clearly the word quantum network has many, many, many branches. You have to pick your battle. Do you mean long distance quantum networks? Do you mean many qubits in one node? Do you mean many nodes, but all in the same vicinity? Distributed quantum computing, for example. Each of these will require a completely different hardware as well as algorithms approach as well. So we have to identify what works best in terms of what is available and what we'd like to achieve. This is a sales pitch for quantum networks. Interconnects for scaling, they will be necessary. Ultimately, what we're saying is, even if you go down the route of, say, quantum computing, monolithic quantum computing, there will be a day where your boat is not big enough, right? And you always need a bigger boat. You always make a bigger boat, but at some point you can't anymore, and you have to go to the next stack. That connection is an interconnection, and that has to be quantum. So I don't care if my fiber has to go 50 kilometers or 2 millimeters. It is still a quantum connection, and therefore everything we're developing for quantum networks is going to be applicable. So there is some motivation for that. And finally, we're going to need a lot of non-quantum expertise. Everything that we're doing, we talked about in the panel today as well, it's not the qubits, it is the wires going down the fridge that will stop you. It's not the photons and the no cloning theorem, it's the absorption in the lines that's going to stop you. Something non-quantum is stopping you. So we need to make sure that we learn a lot from our non-quantum experts, friends, so that we can develop it going forward. With that, I'll stop. I think that's plenty of time, and I'll thank you for your attention.